Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeOCHemISTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Rich Goldfarb about the sci-fi and facts of orogenic gold. Rich Goldfarb is the director at Goldfarb Global Gold and retired USGS. Rich, welcome to GeoChemistry.
Thanks for having me.
So, Rich, you provide me with a rich work history that I'm not going to even try to summarize for our listeners. I think something powerful, though, is a large volume of the literature about orogenic geochemistry now has your name on it somewhere, as well as intrusion-related gold. Yet you come from relatively humble origins. So could you talk us through how you got started in geology and geochemistry and ultimately how you were able to retire or how you were unable to retire from all the engagements that you get asked to be a part of?
Yeah, it was a long, strange trip, Sam. I grew up on the pavement of New York, never had a class in earth science, didn't know what it was. And I was in undergraduate school at a place called Bucknell, and I was a math
Fancy.
major. And I hated it. It was all these calculus things I couldn't understand and stuff. And beginning of my sophomore year, people listening to music across the hall from me, and I went in their room and I was just, what are you majoring in? This math sucks. And when I said, I'm majoring in geology, and I said, what's that? And he said, we just walk around the woods and drink beer. I said, that sounds really good. So I signed up and ended up in geology. And he actually went on to be one of the best bagel bakers in California. But my background then in geology undergraduate was I was doing geomorphology, looking at water chemistry and different land uses in rural Pennsylvania and how that affected the geochemistry of the waters and different runoff of nitrates and phosphates. And so I thought, wow, this is cool. Maybe I'll go into fluvial geomorphology. And at the time, music was really good in San Francisco. So I decided to go to grad school in Berkeley and get my PhD in fluvial geomorphology with
No
Luna
big deal.
Leopold, who Luna was one of the gods of fluvial geomorph. He wrote the book on it. Brilliant guy. It was Aldo Leopold's son who wrote Sand County Almanac. And so I went out to Berkeley and I lasted about 2.5 terms at Berkeley. It was an interesting time. We had Hell's Angels and Black Panthers and all sorts of protests. Patty Hearst was tied up in a closet in the room next to me after she joined the SLA Army. So a lot was
Next to
going
you,
on. So yeah,
I watch documentaries on this stuff. Oh my
oh yeah,
God.
it was incredible times. If I learned to survive then in Oakland, I could handle anything. But after about 2.5 terms, and I learned a lot from Luna Leopold, it was just too much fun going on in San Francisco. And I decided maybe it's time to move across the bay and drop out. And Luna Leopold said I was making a mistake. But actually, the graduate advisor at Berkeley at the time was one of the great geochemists of our era, Hal Helgeson. He was a bit extreme, but pretty amazing. And Hal said, yeah, that's the right decision. Just go to San Francisco and have fun. So I moved over to San Francisco, had a great time listening to music and hanging out with friends. I got a place near Golden Gate Park. I got a job as a bellboy at Fisherman's Wharf. And from there, I got a job as in the janitorial service at San Francisco State University, where I was in charge of the crew cleaning the Venetian blinds for all the classrooms. But at the same time, I did all my classwork to a master's in urban planning and thought I was going to be an urban planner. But after a while, I was getting tired of cleaning blinds and I started looking in the San Francisco Chronicle for jobs. And I got hired at Lawrence Livermore Laboratory This was probably sometime middle of 1978 when they were getting the NORI program going, the National Uranium Reconnaissance Evaluation Program, or as we called it at the end, No Uranium Results Ever program. And the good thing about that was number one, I learned all about the geology of the West. My job for Livermore was in the 7 western states. They were in charge of the exploration geochem program, and I got to follow up and check the contractors in all the 7 states. So I learned about a lot about geology and geography and everything, traveling around the 7 western states, which was a great opportunity. And the second thing that was great working at Livermore and is so important for young people is I met my mentor there. There was a young geologist who had taken over that program named David Leach. David Leach is an incredible geochemist and probably the father of lead zinc understanding of MVTs and clastic dominated, what they used to call SEDEX type lead zinc deposits. And Dave's come to be my mentor at Livermore. But eventually, because of government bureaucracy, Leach gave up the program. They gave it to Savannah River Laboratories. They couldn't deal with a bunch of us geologists who wanted to do science at Livermore. And that was the end of the program. So Dave Leach went on to the USGS in Denver. And I decided, as much as I liked the Bay Area, it was time to do something else. And I went over to Reno because they were giving a ton of money out at the time for master's degrees in geohydrology. So I went to Reno, and for 2 years through the Desert Research Institute at the Mackey School of Mines, I ended up getting a master's degree in geohydrology and never used it since. I was graduating in geohydrology in May 1981, and I got a call from Dave Leach, who was at the USGS for a few years there. And he said, the person who runs the exploration geochemistry program for the USGS in Alaska just quit. If you come, you probably to Denver, you can probably get hired by the minerals program and run this exploration geochem program in Alaska. And I said, wow, Alaska, that would be great. I know nothing about mineral deposits, though. I never had a class in ore deposits. And Leach told me it doesn't matter because it's the government. You don't have to know anything. So I,
I was thinking the same, but continue.
so I loaded everything I owned into my Ford Pinto and drove from
Oh my
Reno with
God.
my new master's in geohydrology over to the USGS in Denver. They already had two student assistants hired who turned out to be great friends of mine forever and ever. Everything was set up. There was a helicopter contract for 11 weeks in the Chugach and Kenai Mountains of Alaska. And a few days later, I was on a plane with the two students up to Alaska to do my 11 weeks field study. I knew nothing about Alaska. I knew nothing about the geology. I knew nothing about the ore deposits. And for the next 4 field seasons, I ran the exploration chemistry program on the glaciers and ice fields and the fjords of South Central Alaska and Prince William Sound for the USGS, and realizing I was doing stream sediment exploration to help understand mineral resources. In my spare time, I went to University of Colorado here, where I live in Boulder, to get my PhD in economic geology. So I was learning on the job. And also at Colorado, they had a great program in glacial geology. So also working on glaciers in Alaska, I also did a lot with glacial geology, and everything just fit together real well. And so you never know where you're going to end up. I went from fluvial geomorphology in one school to urban planning in another, then to get my degree in geohydrology. And I never thought I would work in mineral deposits. I never had a class about ore deposits. And next thing I was doing economic geology for the USGS in Alaska, which really was a dream job. I spent 35 plus summers up there, got to see a hell of a lot. It's just an incredible experience. And we had a great team doing exploration geochemistry in Alaska at that time. People like Karen Kelly and Bob Eppinger and many of the exploration geochemists from our eras in the 80s and 90s and into the 2000s. And it was just a lot of fun for all of us growing up in the Alaska program of the USGS. And doing exploration geochem forced all of us to really learn about ore deposits because you have to tie mineral deposits in with understanding of exploration geochem because that's why you're doing it.
Yeah, and through it, now thinking back on your little library of papers that you have going, especially the IRGS deposit style, the intrusion related gold, that wasn't really something that was necessarily recognized
No,
back when you started.
even before the intrusion-related gold, which we can get into later, even the orogenic gold deposits weren't recognized. You know, in
Mm,
the 1970s, brilliant guy in Canada, Bill Fife, put out what may be the best book on gold existing, and people don't realize it. It's called Fluids in the Crust, and it's a book from the 70s by
we love
Elsevier.
fluids.
And it really is helps you understand ore deposits. But that was in that book, Fife talked about, when you cook up a rock, you metamorphose a rock and say it's a metapeolite, 3 to 4% of that rock can change to fluid. That's a buttload of fluid in a mountain range. People don't realize how much fluid is produced during metamorphism. And from that initial work by Fife, people like Dick Henley in New Zealand, and then Phillips and Groves in Western Australia, and Kerridge with Fife in Canada, started looking at mineral deposits related to metamorphism. And really, from Superior Province in Canada and Western Australia, Yilgarn, the first articles were coming out in the early 1980s on gold related to metamorphism. And there was no name for it at the time. It was just gold and metamorphic rocks. And as I was working up in Alaska, when I was working in southern Alaska doing this exploration geochemistry, all the gold deposits there along the coastal mountain ranges were simply called epithermal gold deposits. That's because any gold deposit was called epithermal. They were doing the initial fluid inclusion studies at the time, and people were studying secondary fluid inclusions that homogenized at 150 and 200 degrees. And they said, oh, these must be epithermal. And they were getting bulk hydrogen isotopes and said, oh, yeah, that's meteoric water. And we can get into that later. But so the models were epithermal. And then I started collecting all these stream sediments and glacial sediments, maybe 5,000 across south central Alaska over those 3, 4 field seasons. At the same time I was doing this, Marty Miller, she was one of our best young geologists up there, she was putting together the first metamorphic map of southern Alaska. And as we started putting everything together for mineral resource assessment, we noticed all the gold anomalies in the sediments were solely in the green schist facies on her map. There was nothing in the lower grade rocks, nothing in the higher grade rocks, even though there were granites all over the place. And we said, these aren't epithermal deposits. This is what people are seeing in the Precambrian cratons also. These gold deposits that are forming in metasediments and Phanerozoic belts are the same things. They're metamorphic gold deposits. And that's what got us going on this model. And the same time we were doing this, a woman named Leslie Landefeld was doing the same thing in the California Mother Lode, coming up with a similar argument. And that really got us thinking about gold deposits related to metamorphism in California. Now, at this time, there was no name for these. And the USGS was just starting to put out model books. And there was a preliminary model book in 1981 put out by Ralph Erickson. It's a USGS open file that came out 5 years before the Cox and Singer famous model book that's a USGS bulletin. And in that initial open file preliminary model book, a guy named J.K. Bulkey said, there looks like an association between the Phanerozoic and Precambrian deposits, which at the time people had as totally different deposits. He said they're all related to metamorphism, and he called them orogenic gold deposits in there. It was the first time that was used. So as we started writing our papers, in the mid 1980s, we started calling these orogenic gold deposits because they needed a name that was universal. And at the same time, Canadians were calling these mesothermal gold deposits after the Lindgren mesothermal classification. But if you go back to Lindgren, most of what he called mesothermal was 2 to 300 degrees and only 1 to 3 kilometers depth. And the only orogenic gold deposits are deeper and most are hotter. So that's why we tended not to use mesothermal and like the term orogenic that Bulkey had coined. And that name stuck once we got into the 90s and mesothermal started disappearing. So that's how we really got all this going. But till we were doing this in the 80s, there was no such thing as orogenic gold deposits. Everyone was just calling these lode gold or epithermal, and they must be related to a hidden granite somewhere at depth.
That's so fascinating because I think I just took for granted somebody that was born in 1987, went to university in the mid 2000s. I took for granted that orogenic was just so well established. It must just be from the beginning of geologic time, that we knew that word. And I didn't realize that it was so recent, actually.
If you look at any textbook prior to 1985, and certainly prior to 1980, every gold model is related to different distances from granite. Closer ones were called hyperthermal, further away mesothermal, and most distant epithermal. And really, there wasn't a lot related to any other process. There was in the 70s, another type of model came out where some people would say, well, there's no granites around. Maybe there's a way to do it without granites. And there was a model called lateral secretion that was big if you look at papers on gold in the 1970s. And what it said was everything moved into these shear zones locally out of the wall rocks and secreted in the gold and all the silica and all the carbonate. But by the early 1980s, people like Kerridge and Phillips did a lot of mass balance calculations and said, you can't locally derive through lateral secretion these kind of gold deposits. And that model fell out of popularity. So it was really in the mid 1980s that this whole orogenic gold model came together. And before then, if you pick up gold books when the price of gold started going up in the early 1980s, they're books on Precambrian gold and greenstone gold, banded iron formation, Biff gold, turbidite hosted gold deposits, slate hosted gold deposits. All these were different deposit types. And it wasn't until the mid to late 1980s, just 35, 40 years ago, that these were all put together into one group as orogenic gold and realized they form by the same processes from the same type of fluids.
Yeah, so interesting. And I think what's also interesting, I find reading the literature today, talking to explorationists today, is that no matter really what element we're talking about that we're searching for, we're really obsessed with finding causative intrusions. And particularly in the case of orogenic gold, that's not necessarily important. But yet we're still pretty obsessed with it.
Yeah, geologists like point sources. It's
Mm.
hard as we can get into a little bit of talking about a regional fluid. People don't understand that. And a lot of people don't understand how much fluid can be created during metamorphism. And there was a famous economic geologist named, more a volcanologist, geochemist named Walter Giggenbach. He
Oh,
gave
I know
the
him.
Okay, he gave the SCG Distinguished Lecture in 1992, and it's in one of those SCG special pubs. And Giggenbach's lecture said, the thing about economic geologists, no matter what, if they can't find the source of a mineral deposit nearby, they put arrows pointing downward to say there must be a magic granite at depth. And
Yeah.
he was a magmatist, but that's what geologists like to do. They
Mm.
like to point to a point source. And if you want to publish a paper and you don't know where something's coming from, and you have a granite 10 kilometers away, even though it may be a totally different age than your mineral deposit, people tend to sometimes even throw out the geochronology and say, there's a granite nearby. That's the one source I can come up with, rather than say, there's just a regional fluid moving around in the crust. There are a lot of fluids in the crust, and it doesn't have to come from a point source.
So we should just basically be less afraid of talking about fluids. I love it.
And we should try to understand fluids. For me, some of the most interesting papers that are published are papers about subduction zones and fluid movements in subduction zones, and trying to understand where fluids come from, how they move around. There's a lot of misconceptions about where fluids come from. I think besides magmatism, and we could talk about this in a little bit, many workers today are now saying orogenic gold deposits or most gold deposits form from fluids escaping from the mantle. And that makes absolutely no sense. You cannot have a fluid coming out of the mantle to form a gold deposit. So a lot of finger pointing at sources, but without thinking about really what's going on and what can happen. But understanding fluids, how fluids move in structures, people like Rick Simpson and Steve Cox, their work on fluids and movements of fluids in the crust are so important to understanding gold deposits. Not even looking at papers on ore deposits, but just on structure and fluid movement are so critical because that's what we're understanding when we look at ore deposits.
Yeah, and I think I'll just close a loop for our listeners because it's a really random thing to know. The reason I know so much about Gegenbach is because he designed these little bottles, which he used to sample gases on White Island, particularly a volcano in New Zealand. However, many years later, I applied the same sampling methodology with the research group I worked in with Willie Williams Jones at McGill. And we did this all at the Cowichan volcano. So there we all were sampling gases. It was also at Simon Fraser University. We were sampling gases with Gegenbach models
No, that's
on an
good.
active volcano. No big
And
deal.
people should go look at some of Giggenbach's stuff. A
It's
magnetist
fascinating.
who
Yeah.
says not everything has to point to a granite.
And I find that interesting too, because here I was applying it to volcanism. But I read those papers so long ago now, but if it wasn't talking about actual methodology, I probably wasn't interested so much in it. But it's interesting to hear that there's a whole nother side of Gegenbach that I didn't even know. So look at that.
Yeah.
All right. I think that this has been super interesting. I'm so glad we plumbed those depths, pun intended. We will circle back to all that. But for now, I want to thank you for sharing this story. And I hope that everybody really enjoyed these stories as much as I did. But now it's time for my favorite segment, which is tea time. So, Rich, the kettle is hot and it's time to spill your tea.
Sounds good.
Okay. What's your tea? What'd you bring us?
What's my tea? What does that mean? What's my tea?
Oh my God, Rich, we talked about this before we started. It's just a little piece of gossip that you brought, a little funny story.
Oh, a funny story.
Yeah, just a funny story. It could be a field story, could be what happened in Sydney last weekend or a week ago, which nothing was particularly funny.
I'd have to think about that. A funny story. I got going on a lot of this orogenic stuff. I was working with one of the better young isotope geologists in our
Oh,
field
oh
named Bill
my.
Bigthorn. Good friend of mine, Menlo Park. He left the survey in the 1990s. But the best thing about Bill was he could get real nasty with people. And at the time, there was a lot of controversy on orogenic gold, whether it was metamorphic in origin, or especially how the Canadians were arguing there was surface waters involved, meteoric
Oh,
waters. And so we'd
okay.
go to all these conferences, and there would be a lot of debate and whatever. but I would always make sure Bill was there because you could always tell Bill, that person talking up there and saying things about the meteoric model has said, we're really wrong. And he pointed out how your work is all bad to me and all this stuff. And you could just see Bill getting red and angrier. And then eventually at the end of these questions, whether it was an SEG meeting or a GSA meeting, Bill would just stand up, get a question, and just get so angry at the speaker they wouldn't know what to do. So it's great having a guy like that working with me that you could really use as the nasty guy to stand up and do stuff. And Bill and I are still friends, but the USGS would get somewhat upset sometimes because he would go a little overboard. It was great having a guy like that. We could just point in the right direction. Dave Leach and I would always be able to just tweak Bill and get him going and really get our point through.
I love that.
So it's good to have a fun team.
Yeah, just have a little bit of spice at a meeting. Yeah, I like that. Yeah. I think a lot of when I was first reading, though, first learning about all these things in school and everything, something that I had a hard time conceptualizing was people using meteoric water to describe a lot of things. And I was just like, I'm not really following all of this. And I found that to me, if I didn't enjoy high temperature fluid geochemistry and even low temperature to an extent as much as I did, I think I would have a lot harder time conceptualizing ore deposit formation because of a lot of papers' reliance on the concept of meteoric water for pretty much everything that I was reading.
Yeah, and I think a lot of that, at least in the orogenic world, came from bulk extraction of fluid inclusions.
Mm.
Like hydrogen isotopes have a distinct signature at northern latitude in fluids. If they came from surface waters, they would be very light in hydrogen isotopes, very low hydrogen isotopes. And people used to either, they would take quartz veins and either crush the quartz to get the fluid inclusion waters out or thermally decrepitate. Either way, you would easily get the water out of the fluid inclusion, stick it on a mass spec, measure hydrogen isotopes, and they would always be meteoric. And that's where the meteoric model came from in the 1980s, especially by a lot of Canadian workers. But you have to realize in orogenic gold deposits, 99% of the fluid inclusions are secondary inclusions that have trapped fluids as you deform the rocks during their uplift up to the surface. So those waters are yesterday's rainwater, and of course they're meteoric water, but they were trapped after the gold and the silica were deposited, and they have nothing to do with ore deposit formation. And I think now most people agree with that, but people would like that to measure their hydrogen isotopes back then, and some still even do it today, because that's a quick way to do it rather than picking hydrothermal micas under a microscope, which may take a month to get enough, and then it's extracting the hydrogen out of the micas and measure that. And that often gives you heavy water that is inconsistent with meteoric water, yet people like the simpler, quicker way. And that's why the meteoric water thing was really big back then. Go
Oh,
ahead.
I was just going to say the other thing that people really, I think it's hard to conceptualize, but there's no other better way to do it because it is a scientific term, is when you hear fluid, I think a lot of people think about something that is water-like and not considering the different properties of what a fluid can be. And so that also throws you off. You're just thinking fluid, okay, it has to be water based, same composition, and maybe there's some other components to it, but not considering that there's so many different levels of what a fluid can be.
It can
So,
have CO2, methane, nitrogen, H2S. There are a lot of different volatiles, and they don't all have to be aqueous.
yeah.
And, and that's something also very characteristic of orogenic gold. But that's in the 80s, we were all still formulating this. And it was just great to go out in the helicopter and visit all these old mines, up on the ice fields that no one had seen in 100 years and get samples from those. And that's the day before cell phones, too. So they couldn't call you up or find you until you had no more money and stop flying and stop working. So those were good days of getting away with anything. And another thing for tea time back then, and the one thing I learned, again, having a great mentor, Dave Leach, the way to solve any problem in the government is create a bigger problem, and then you can get away with anything. And a lot of us that were very productive in the USGS over the years was through a lot of creative work where you would give the government the basic work they wanted, their open file, their data dumps, things like that. But to do the science behind the mineral resource work, you had to be creative. And if you were creative, you pretty much could do anything. And that was one of the good things working in the USGS.
So now we'll know based on reading open files who's creative and who's not.
Yeah. And I looked at this, and you might look at some of the acknowledgments in open files from the 1980s. There's some creative names and little sayings in some of the acknowledgments that I probably
Oh,
shouldn't talk about. But yeah, a lot of sort of names snuck in there that the government, when they found out, weren't happy about. But it was all fun back then.
possibly if you didn't have references to Stalin or Lenin, I think generally you're probably fine, right? Just
This
keep
could have
it.
been worse, but
Oh my God.
I won't name some of the acknowledgments, but
We'll
if
talk about it
people have
later.
any questions, they can email me and I'll mention things that have been acknowledged.
Oh my God. I love it. Look, let's just get into it. I think we've already talked so much good stuff about our topic, so that's great. But for this episode, Rich quickly suggested his own paper from, I believe it was just last year, but it's called Orogenic Gold. Is it a genetic association with magmatism realistic? And he supplemented this 35 pager with a slide that he entitled Orogenic Gold Science Fiction, which potentially we could read at some point during this, but probably I'll just post it up on the website so you guys can all have a look at it. Maybe this is just for Rich to know, but when I was reading this, I made a ton of notes on this paper. I was flying DC to Phoenix, and really it took me the entire 5.5 hour flight to do it. But I would say it was so dense, and maybe I was falling asleep at certain points because
Oh,
methods can
no.
get a little, no, I'm kidding. It was just, there was a lot to think about, and I really enjoyed it. For those that haven't read it though, I would say go and do, there's a lot of food for thought in it, whether you agree with it or not. Again, food is food. For now though, let's just get right into exploring this paper through our Q&A. The first question I just wanted to ask you here was, what was the driving force behind you and Ian Pitcairn to write this paper?
I decided I had written my last paper a few years earlier, but I'm not doing a good job on it. And even now, I have a few last papers coming. But one of the editors of Mineral Depositor, Bernd Lehman, who I've known forever, so I owed him favors, said, Rich, can you write us some sort of review paper on orogenic gold? And I said, there's so many review papers, and I've written two or three. I don't need to write the same thing again and whatever. Can I write you a paper instead about something that I'm pissed off about? And Bert said, sure, no problem. And I said, every paper coming out on orogenic gold now wants to say something new. So even though we've had a model that seems to make great sense relating orogenic gold to metamorphic processes, every paper coming out now in economic geology or mineralium depositor or GSA bulletin now relates it to magmatism or the mantle. And this just makes no sense. So I'm going to write you a paper on that. And Bernd said, okay. And I've known Ian for a long time, and Ian's one of the best young people working on orogenic gold and made a lot of important contributions on movement of metals in crustal fluids as you change metamorphic grades and things like that. And we can talk about that too in a little bit. So Ian was up for it because Ian also didn't believe in the all the stuff that was coming out that just made no sense to us. So it was a model we wanted to put out there, a paper that's not just explained how orogenic gold forms, but how it can't form and why these other models that are being put forward just don't make geologic sense. And so we put this sort of together, and then before even sending it to the journal, I ran it by 4 or 5 friends who are magmatists and said, tell me why we screwed up here. What is wrong? And they gave me some good feedback, but nothing really that they said it made good sense. And they gave us some ideas of things to add. And we sent it to one review. And actually, Bert sent it to Dick Silito, who's a magmatist, to review it. And Dick said, I don't want to touch that. So Dick sent it to this other guy, Blundy, who's an igneous petrologist. And he came back with some reviews that had us rethink some things and tweak it a little more. But then it came out and it, I think, makes great sense. What's frustrating, though, in the year since it's been published, it's got a buttload of references, of citations, maybe 75 citations already in the first year. But if you look at the citations, it's just typical. Out of 75 citations, probably 73 of them said there's a spatial association between gold and orogenic gold and magmatism. And then they reference us because we have a recent paper, Goldfarb and Pitkin 23. And then they go on to say how there's a genetic association and ignore everything we said in the paper. So even if you say it, people ignore it. So people should read it and they can decide to themselves whether it makes sense or not. But that's what got us going on. It's just going, these magmatic and mantle models are just senseless. And so we wanted to put a paper out there where if people want to read carefully, they can reach a decision and see if they agree with us or not.
And that's what I really liked about the paper was that, look, I've worked in a few orogenics lately, but I don't work in a ton of them. And I found what the paper did was it made me think critically about some of the stuff that I was doing because I don't usually think too hard about and the different things I've been asked to do for these kinds of deposits. I have to think too deeply about how they're formed. And for me, I just found that this, plus in the wake of a conference I was just at, and there was a keynote on what was really pushing the magmatic model. And I think after having listened to that, then reading this paper, it just gave such incredible food for thought, really, about just accepting what people are saying to you or you're reading other places and just seeing a really nicely put together point of view from the other side. Guys, you got to read the paper like for yourselves. I just think it reminds us to think critically about what we're reading and not just to believe anything that comes out of chat GPT. So
And just one point on that. Yeah,
yeah.
believing everything is difficult these days because in these days of open access, anything gets published. And if a paper gets rejected from Econ or Mineralium Depositor, you'll see it in another journal, guaranteed 2 to 3 months later. And a young person, a student, or a young person entering industry that hasn't had time to read everything or doesn't have the time, especially in industry. What do you believe? You Google orogenic gold, you get 100 papers, and a third say one thing, a third say another, a third say another, and you're exploring. Do you explore for a certain kind of granite, or do you explore trying to understand the structures? And so it is important as an explorationist to do this, but now that everything's in print, it's so much harder today because you don't know what to believe or not believe. And common sense often is skipped over in a lot of these papers, in my opinion. And that's another thing that got Ian and I writing this was so many of these papers just don't show common sense.
I think that's a really relevant plug, and I appreciate that, and especially saying it here. We've had a few people that have come on the show that have talked about this extensively, and it's just we cannot underlie enough, especially because this podcast is about mentorship. So we can't underlie enough how important it is to just understand what you're reading, what journal it's from, and being critical thinkers about what you're reading. Circling back now to fluid chemistry, because it's something that I love and I always want to talk more about. So in this paper, you talk a lot about fluids, again, which I loved. But
Okay.
while this is a geochemistry podcast, not all of our listeners are geochemists. For here, I just wanted to focus a little bit more on what we mean when we talk about fluid chemistry. I'm going to ask 5 questions really quickly because I think they all lead to the same concept. But if I feel that you've missed one, I'll ask you again. What fluids are involved in orogenic gold formation? How does it have the capacity to carry gold and potentially other metals? And how do we know that these fluids cannot be magmatic in origin?
Okay, there's a lot there.
There's a lot
The-
there, but they're all related. But
yeah,
I'll hit you up if you forgot one.
okay. The fluids that form orogenic gold are different than almost any other fluid. If you go to kaolin, epithermal, porphyry, the fluids are all water rich or water dominant. They're probably at least 98, 99% water. They have limited amounts of CO2 or other gases. They may, if there's a large magmatic component, have a high salinity. In contrast, orogenic gold deposits have anywhere between 5 and 20% CO2. They often have, I shouldn't say just CO2, they have 5 to 20% non aqueous volatiles that generally is dominated by CO2. But in carbonaceous wall rock environments where the fluids may be a little more reducing, that non-aqueous component can also be significant amounts of nitrogen and methane. Also, there is significant H2S, very much less than the other gases, but significant enough. The salinities are also generally low to moderate, maybe 3 to 8 weight percent NaCl. So it's a totally different fluid than that forms most other types of gold deposits, having a lot of non-aqueous volatile species in it. What else can I say about those? It also stands out when you do fluid inclusion work, because if you're looking at orogenic gold, one thing you always see is clathrate. Other gases freezing when you do microthermometry and fluid inclusion work on orogenic gold. That in almost any orogenic gold deposit. If it's a non-orogenic gold deposit, you never see clathrate. You're not going to go into a porphyry or an epithermal or kaolin deposit and see clathrate when you do fluid inclusion work. So right off, that's an easy difference because you just have so much non-aqueous volatiles in the orogenic gold world. So you have a totally different fluid. The fact that you have H2S in the fluid and you have that in any metamorphic fluid is important because the H2S carries gold. At higher temperature fluids in the porphyry world, you have chlorine that can carry the gold, but there's rare cases where chlorine is significant in orogenic gold. Gold is moving as a bisulfite complex. The orogenic gold deposits can form depending on the geothermal gradient over a broad temperature range and a broad pressure range. These non-aqueous fluids can form gold deposits as shallow as 3 or 4 kilometers or as deep as 15 to 20 kilometers, depending on the geothermal gradient. Most of the time, those fluids are depositing gold at 250 to 350 degrees, but they can deposit gold at slightly lower temperatures and be what we call epizonal, or they can deposit gold at somewhat higher temperatures and in what we call hyperzonal environments. And if they're lower or higher temperatures than typical 250 to 350, the mineralogy and the alteration minerals will change some, but they'll still be orogenic gold deposits. They'll still have a lot of non-aqueous volatiles in those. So I guess that answers your question about what the fluid chemistry is of orogenic gold. I guess the next thing is how that fluid would be produced. Is that the
That's a good
next
one.
thing?
Mm-hmm.
That fluid would, as I said earlier, 3 to 4 volume percent of a rock changes the fluid during metamorphism. That can be peelites, that can be oceanic volcanic rocks that have been serpentinized and altered on the ocean floor. But rocks, marine rocks undergoing metamorphism, have a hell of a lot of fluid in these. And between green schist and amphibolite facies, you can break down chlorite and other hydrous minerals, produce a lot of water. These fluids, as I said, have a lot of CO2 in these. We're in active continental margins normally, so we don't have a lot of carbonate. That's more in passive margins. But we have a lot of organic matter. You start increasing the grade of the metamorphic, of the organic matter, and you lose carbon. And so you can have CO2 and methane in the fluid. And then the sulfur is always in a metamorphic fluid or this kind of fluid because you always have, if you look at a rock, say you pick up a carbonaceous shale, it's going to have 6, 8 ppb gold. If you pick up a greywacke, it's going to have 3, 4 ppb gold. But that gold isn't in the quartz, it's not in the feldspar, it's not in the mica. It's in those opaque under the microscope, which are your syngenetic to diagenetic pyrite grains. If you zap those with a laser, they might have 500 ppb gold or a part per million gold. So when you go from green schist to amphibolite, besides releasing water and CO2, at the same time the sulfur is coming out of the pyrite because the pyrite's converting to pyrrhotite as you go up metamorphic grade, and also the gold that's in that diagenetic pyrite is coming out, and the arsenic is coming out and goes into your metamorphic fluid. And so all these main ingredients of an orogenic gold fluid, H2O, CO2, H2S, gold, arsenic, are all coming out during this metamorphic facies change. And basically, orogenic gold deposits form from a regional fluid, and a lot depends on the structure of the crust, whether or not you're going to have an orogenic gold district or not. If fluids are focused into a major structure, fluids tend to move horizontally down structural, their pressure gradients into large faults. They'll move up there in seismic events and form your gold vein systems. However, if you don't have large structures, you still create the same amount of gold-bearing fluid during metamorphism, but the water goes everywhere into little structures and the fluid goes everywhere. So you may not have a big deposit. That's why we have gold districts such as here in North America, the Seward Peninsula or Nome that had 8 million ounces, or the Klondike in Yukon, Canada that had 20 million ounces of alluvial gold. You have great alluvial fields, but never produced any lode gold because you have thousands and thousands of little orogenic gold deposits. It may have 100 ounces of gold or 1,000 ounces of gold or 5,000 ounces of gold. But what you don't have is focused fluid and a large lode gold resource, but you got the geomorphology, such as alluvial geomorphology or glacial concentration and beach movement in the case of Nome to form large alluvial deposits. So you need to focus that fluid and you form an orogenic gold deposit. It's just regional fluid flow that's part of metamorphism, and any metamorphic belt that's not high pressure, low temperature will always have orogenic gold forming. So that's the story on how fluids are produced in the orogenic gold world. And I can go on to the magmatic world, but did I skip anything on the orogenic gold fluid
I
story?
think the only orogenic thing that you skipped that is important for people to hear is we've talked about their transport. How did they drop out of solution? What is the trap, if you will?
Okay, the trap is interesting because people like to have the precipitation mechanism.
Hmm.
There never is the precipitation mechanism. Most orogenic gold forms under what's called mesozonal conditions at 6 to 12 kilometers depth. In those cases, And Rick Simpson, Francois Robert, and others have talked about this. You have a lot of seismic switching, a crack seal kind of gold formation. The orogenic gold, you build up pressure till fluid pressure exceeds rock pressure as your fluids are moving into these big faults. Then they will fracture along these big faults, and you'll go from 3 to 4 kilobars pressure transiently down to a few bars, basically atmospheric, at great depth. And when you do that, those large pressure drops, silica solubility greatly decreases, and you lose all that silica that's in that metamorphic fluid. That's why we have all these quartz veins, big quartz vein formation, often at 6 to 12 kilometers depth. What's different, though, is that pressure drops at those temperatures don't cause gold solubility to decrease. Gold solubility stays the same no matter what the pressure is here. So other things get the gold out of solution. And when you have large pressure drops, you change the chemistry a little of the fluid. You may unmix the CO2 in water. It's not truly boiling like of water, it's unmixing or immiscibility. The non-aqueous volatiles will separate from the aqueous volatiles. That will change the chemistry of the fluid also. And when that happens, you change the FO2 of the fluid, and you also change the pH of the fluid. The fluid may react during these pressure drops and boiling with or immiscibility with the wall rocks, and you have sulfidation of iron in the wall rocks. So you have all sorts of chemical changes happening at the same time, changes in sulfur, FO2, and pH. And all those can help get the gold out of solution at the 6 to 12 kilometers depth. Now, at greater depth than 12 kilometers, you're in a more ductile regime. So you don't have the fractures that the fracturing, the hydrofracturing you normally have. You don't build up the big pressures. So there, almost all the gold deposition is by sulfidation. That's why a lot of the deeper, more high temperature orogenic gold deposits are in banded iron formation or iron-rich rocks. You don't have a lot of quartz veins. You may have a lot of silicification, but it's more replacement disseminated style mineralization below about 12 kilometers. And above about 6 kilometers, you're very brittle. You still fracture the rocks, but you tend to get more stockworks and brecciation. But many different things can get the gold out of solution, and there's never just one thing that gets the gold out of solution. Unlike magmatic deposits, what you doesn't get the gold out of solution are temperature drops, because you're not looking at a steep geothermal gradient away from a causative heat source like a Pluton. You're looking at regional fluids where the geothermal gradient might be 20, 25 degrees per kilometer. So there's almost no temperature decrease. And we know that because we can look at the largest orogenic gold deposits on the planet that go 2 to 4 kilometers down dip, and the fluid inclusion temperatures don't change from top to bottom, and the mineralogy don't change from top to bottom. So we know there's no change in temperature that is occurring. And unless you have a lot of chlorine, gold solubility also doesn't drop much with temperature drop when it's not carried in chlorine in a hydrogen sulfide complex without a lot of iron and chlorine present. Temperature isn't going to get gold out of solution. So unlike magmatic deposits, temperature is the one variable that doesn't come into play with gold deposition in orogenic gold.
That's so interesting. And I feel like we've just canceled out questions 4, 5, and 6. We've talked about them already. Is there anything that you just want to say just to underscore your feelings on that? There's just no potential way for magmatic fluids to be involved in orogenic, like a one-liner or
Yeah.
something.
Oh, no, if we got
Okay, let's
time,
do
we'll
it.
touch on that because that's an interesting issue. Too often, economic geologists ignore what the petrologists tell us. Igneous petrologists have recognized for a long time that water, the solubility of water in melt depends on pressure. At high pressure, water is extremely soluble in melt. So that's why water is not going to come out of melt at high pressures till you get to about 1.5 kilobars or 5 kilometers depth. In a hydrous magma that has 4 to 6% water, that would form most porphyry deposits. That water is dissolved in magma. So you get these orogenic gold deposits forming at 5, 6, 8, 10 kilometers. They can form from magma because from a magmatic fluid, because any fluid will still be dissolved in the melt. And even if a little amount of fluid does come out of the melt, it's not going to be coming out of the crystallizing sides, but it moves up the mush in the melt up to the brittle cupola till it can fracture it. That's why Dick Sillitoe noticed this in the 1970s, that the deepest economic porphyries for gold are at 3 kilometers depth. Without the gold, maybe some of the copper porphyries are at 5 kilometers, Somali at 6 kilometers, but the deepest gold bearing porphyries are 3 kilometers. And you don't form porphyry deposits at the depths of most orogenic gold because the water is still sitting in the magma. So, how you can possibly get a fluid out of magma at depth to form orogenic gold deposits at those depths makes no sense. And that's the point. You can point to a nearby granite that has the same age, but that granite can't release fluid with gold to form a gold deposit because that fluid is still dissolved in the magma. You don't lose large fluid volumes till you get to low pressure. That's a fact that every igneous petrologist has pointed out. You can go to some papers by an excellent geochemist, Jake Lowenstern, from 25 years ago, showing how early fluids coming out of melt as it's rising are almost all CO2, but small volume. And you don't get large volumes of aqueous fluid coming out till you get till about 5 kilometers depth and shallower. So that's the problem with the magmatic model. And now everyone seems to jump on the mantle model from all these isotopes we don't understand, lithium, copper, rare gases. And everyone's saying, now we know orogenic gold has come from the mantle because our lithium isotopes or our helium ratios show a mantle connection. First off, who know, and mercury isotopes are really big now. But things like mercury or helium, these gold deposits form along large structures that do go to the mantle. And so just because we have some helium or mercury coming from the mantle, that doesn't mean that the water and CO2 and gold are coming from the mantle. You lose things that are very volatile, some of these gases, from the mantle. But what you don't lose from the mantle and makes a mantle model impossible is these models, if they're not magmatic, say fluids are streaming from the mantle up these big faults based on this isotope data. But if you're at mantle temperatures, water is not going to leave the mantle as a fluid. Wall, above 650 degrees, water will cause the rocks to melt in the mantle, and the water will be dissolved in the melt that then comes up as plutons that can form your porphyries at shallow levels. But you're not going to have water coming out of the mantle because if you have water there, it's going to melt the rocks and be dissolved in magma. And I think any mantle person will talk about that. At one time, and I don't know if people really believe it, they talked about fluids streaming from the mantle, but those were all CO2 fluids because even back then, when this came out in the 70s, people knew water at those temperatures melts rocks and goes into melt. So both mantle and whatever you want to call it, magmatic models don't work at the level of orogenic gold for formation of orogenic gold deposits. It's physically impossible to have that water coming out of a magma at 8, 10 kilometers to form a gold deposit.
It's a lot to think about. for Friday. Guys, we're recording on a Friday. No, it's really fascinating. I love, as we said, I love talking about fluids. So this is super interesting. And it's a great point, though, that as economic geologists, as geochemists, we can't lose the igneous petrology, the metamorphic petrology, and all the work done in those fields along the way. So it's a great kind of first principles kind of discussion to have.
And anything is possible. And sure, there's a lot of anomalous deposits, and some we call orogenic deposits may have formed a little shallower, may be related to an intrusion, and then thus would be some sort of in the porphyry world and not really related to the orogenic world. But for the most part, if you're going to point to a granite for your orogenic gold deposit that formed at 6 to 12 kilometers, which is where most of them have formed, explain how that granite released water at those depths or below those depths to form a deposit above, and why it looks like it does rather than your typical fluids escaping a magma and forming sheeted veins or stockworks in the roof zone of the granite rather than forming
Yeah.
something that looks like hundreds of fluid pulses along a shear zone, which is
I think
along a
that's a really
vent.
good point too.
Yeah,
Yeah. The actual style of what you're looking at.
yeah. You
Yeah.
look at orogenic gold, and whether it's the California Motherlode Belt, which are the large belts in the Superior Province, those are patterns that are much different than magmatic deposits, which don't tend to line up for hundreds of kilometers along major deformation zones. I'm sure we could talk about the Andes having porphyry belts, but we're talking about a broad range there. Well, we have porphyries along a linear mountain range, but not along a major fault system for hundreds of kilometers. What we see in the orogenic world isn't the kind of fluid flow we see from the tops, the granites that are lined up for hundreds of kilometers every 10, 20 kilometers along a major structure. It just doesn't make sense. And people just like to say this isotope or this nearby granite or these ages say it must come from the granite, but they don't explain how that happens because you can't explain it, at least in
And
my opinion.
I'm like imagining all the Andean porphyry work that I've done in my career, and I'm just like, yes, considerably different in alteration, in mineralization, in just form in general compared to all the orogenics that I've seen in my career as well.
But
Yeah.
when I say this, that's why I say the Andes. I say these don't line up in a linear belt like orogenic gold. People point out the Andes are a belt of porphyry. Yeah, but they're not the same as the Abitibi that sit right along those two major breaks, deposits after deposit. These things are spread up and down the Andes, but not along one major suture zone between blocks, a terrain boundary, or whatever
And
you
they're
want to
also
call
more
these.
so like these plug-like features. Yeah, the individual deposits aren't, there's multiple, we can get into it, but there are these plug-like features that are well sorted, if you will, whereas these orogenic belts, the Abitibi, the Africa, etc., they're very structural. They're vein features and everything, and yeah,
Yeah. So to
much
me, that's
different.
my
Yeah.
problem. You know, I have nothing against magmatics, but
Mhm.
I just don't think some of these that we're calling orogenic gold, you can point to a magmatic association, and that's important for your exploration. Because if you want a magmatic association and you're out there exploring in covered land, you're using geophysics to look for a certain age and type of granite undercover, and you're ignoring certain structural factors that are key for exploration.
Yeah, and I think now that we're starting to talk about this, I think it's a nice time to take a little pivot here and talk about this large discussion that's being held in trace element geochemistry and how these elements can be indicative of a fluid source. I just sat through a great presentation about all these different magmatic pathfinder elements and how it was indicative that this orogenic system was definitely of magmatic origin, even though it was, like I said, an orogenic. That said, keeping in mind that no one genetic model is possible, how can you explain that certain anomalies that we're seeing in these deposits, for example, tellurium and bismuth, are not indicative of a magmatic source?
That again is part of the science fiction. in gold geology. Basically, tellurium, bismuth, and tungsten, beginning about the year 2000, all of a sudden were assumed to be indicative minerals that your gold deposit has a magmatic origin. That's because about 2000, in the late 1990s, Fort Knox, a deposit in Alaska, went into production. Fort Knox is a part of a unique belt of reduced intrusion related deposits where you don't have your normal porphyry systems that are associated with copper and gold, but you have reduced intrusions that may have picked up some of the country rock in the intrusions. And these typically have tin and tungsten associated with them, but they've been recognized for low grade sheeted veins in what's called the Eastern Tintina Belt at Fort Knox and a few deposits over in the Yukon. Generally, this is the only productive area of these we know about in the world. But when Fort Knox went into production, those sheeted veins have almost no uh, sulfide, less than 0.5%. So you could really see the tellurides and the bismuthinite and native bismuth and the scheelite in the quartz carbonate veins at Fort Knox. And since Fort Knox was this new deposit type, reduced intrusion related gold system, all of a sudden people said, well, tellurium, bismuth, tungsten are indications of a magmatic source, forgetting that number one, we never analyzed before Fort Knox for low level bismuth. Low level bismuth was always present in orogenic gold because bismuth substitutes for lead in galena, and there's always traces of galena in orogenic gold. And if you always analyze low level, we had done that in the past, which we started doing, we'd get 5 or 10 parts per million bismuth. Tungsten. Scheelite was mined on the South Island of New Zealand from the orogenic gold deposits. During World War II, before the gold was mined. There were no granites anywhere in the Otago schist belt, but scheelite was mined from the veins. Tellurium, gold telluride, calaverite, is named after the Calaveras area in the California Mother Lode, a classic orogenic belt. So tellurium, bismuth, tungsten are always in orogenic gold deposits, but once Fort Knox came into production, people started analyzing these three elements, and all these orogenic gold deposits were now being reclassified as intrusion-related deposits, even if there were no intrusions around, because they had some tellurides or bismuth or tungsten, which are always present. Things like tungsten are, if you have diagenetic rutile, and at the green schistoamphibolite boundary, Ian Pitkin and some of his coworkers have shown rutile converts to titanite. There's a lot of tungsten in rutile. Titanite can't hold it. So tungsten moves in a metamorphic fluid. Tellurium is often enriched in diagenetic pyrite. So the gold in arsenic comes out during metamorphism, and so does the tellurium. So tellurium, bismuth, tungsten, it's just fiction that they mean anything about magmatism. They can move in moderate to high temperature fluids in either environment, and they're in magmatic systems and they're in metamorphic systems, and there's no indication whatsoever as pathfinders saying these fluids or these deposits are sourced from a granite.
That's fascinating. And I think also that said, when we first started analyzing back in the 70s, 80s, this new deposit style, the orogenics, labs weren't analyzing for these. And it only is until very recently that we have these low levels available for tellurium, tungsten, all the rest of them, right? So it's also a matter of improved technologies. I
But
love the history though.
yeah, if you look before 2000, there's no papers saying tellurium or bismuth are
Mm.
indicators of a magmatic deposit. They were just whatever, and whatever way you wanted to have the mother lode form. Some of these deposits, like Kensington and the Juneau Gold Belt, 90% of the gold is present in calaverite. Tellurium is very common in orogenic gold, and is going to be a byproduct as we use more and more tellurium as a critical element for solar panels.
And so Thinking about it in a more practical sense, talking about people using Pathfinder geochemistry to detect
Yeah,
these orogenics, is it more important then to understand the terrain, the actual deposit that you're in versus this generalized suite of orogenic Pathfinder elements?
absolutely. One of the biggest mistakes people make is trying to understand, trying to just say, this is going to be my pathfinder element, a couple of elements for orogenic gold in my gold province, because every province is different. And that's why it's so important to go out and do a geochemistry pilot survey if you're going to use geochemistry in soils or waters or stream sediments first to see what your pathfinder element is. In Western Australia, the broadest halos for orogenic gold in the Yukon Craton Pasielu showed years ago was tellurium. Where I've worked in Alaska, arsenic and tungsten have given the broadest halos. Other places, antimony gives the broadest halo. So that's why it's so important to look at your sample media and different possible elements in pilot studies or orientation studies, and then go out and apply pathfinders. And in orogenic gold, pathfinders is so important because they give such broader halos than gold, which is not as mobile. And low level gold is expensive. And if I was going out in an area to do exploration, the first thing I would do as a pilot, find my pathfinders, go out and do regional surveys with those pathfinders. And where those pathfinders show areas of interest, then I would spend the money on the low level gold. But doing some of these pathfinders first before you do the low level gold, because they have such broader halos, always to me seems to be the more critical way to approach your geochem exploration.
Said, I have nothing to add.
Okay.
Look, we chatted a little bit about isotopes and source regions, but I, for some reason, have quite a little following there with isotope geochemists, and I don't want to leave them hanging here. And you did write quite a little bit about them in the paper that we're talking about today. In the spirit of not wanting to alienate these beloved members of our community, by not addressing some of the findings of the helium, the noble gases, oxygen, sulfur, and other isotopes that prove a magmatic component to orogenic gold formation. I know we already talked a bit about this, but anything else that you want to say to expand upon steps that they're
Yeah.
doing now and what they mean versus your opinions of maybe what we should be doing?
Yeah. Isotopes are a tool and should be tied with anything else. I certainly think the noble gases, we don't really understand what they're saying. We get broad fields. They could be coming up these deep faults from anywhere and being trapped in inclusions. Getting these bulk noble gases just don't mean a lot to me. I think one thing that really sticks out to me are oxygen isotopes. They've always been useful because the orogenic gold deposits really stick out as being isotopically heavy in oxygen. And in fact, years ago, when we were looking at the epizonal deposits in southwest Alaska, that were massive stibnite and cinnabar deposits. Now one of these is 40 million ounce Donlin Creek. The shallow orogenic gold deposits have oxygen isotopes of plus 25, plus 30, because they form at low temperature where there's more fractionation between fluid and quartz. And so you can tell right off if it's in a magmatic world or an orogenic world if your oxygen isotopes are that heavy. Sulfur isotopes are all over the ballpark. That's something we showed in Alaska in the 1990s from different age deposits around Alaska. They depend on the age of the host rocks being metamorphosed and the sulfur isotopes of the sulfur in those rocks. There's no, a typical magmatic deposit might have sulfur between -3 and +3. A magmatic deposit from a mantle would have a rather consistent sulfur isotopes. Orogenic gold deposits have sulfur isotopes anywhere from +10 to -15, depending on what the age of the source rocks are, which is dependent on the pyrite and the sulfur coming out of the ocean of a given age. So sulfur isotopes are all over the ballpark. They're not like magmatic sulfur. And then radiogenics. Just take simple lead. This is something we said 30 years ago that people don't care about, and they still say, my lead isotopes or my neodymium isotopes show that there's a magmatic component. These are Rob Kerich, great geochemist, pointed this out decades ago. Many of these components are not moving in low salinity fluids that form orogenic gold, like lead is not moving to a large degree. That's why base metals are never mined for orogenic gold deposits. So, for instance, lead isotopes, it's been shown in many places, Canada, Juno Gold Belt, Jiaodong Peninsula in China. On opposite sides of the fault, lead isotopes of a given deposit formed on the same day but in different host rocks will have totally different lead isotopes. That's because most of the lead isn't coming in a solution. You have alteration of the wall rocks, elements like minerals like feldspar break down, release their lead. Some of that lead ends up going in the galena, just like the iron also reacts with sulfur to give you pyrite. And that sulfidation lead gives you the lead of the wall rocks. So doing these radiogenic isotopes on elements that are not moving to a large degree in the fluid and are mainly coming out of the wall rock give you real dangerous answers. So a lot of these lead isotopes or other isotopes, when you host it in an igneous rock, in a granite, and they match the lead isotopes to the granite, are not telling you the fluid is coming out of that granite. It's just saying you the lead in the trap is being contributed to the fluid or into the mineralization from fluids and gold that have been transported from elsewhere. So we have to be careful with radiogenic isotopes.
That's super interesting. I have nothing to contribute as my isotopes are horrific, but I
And I'm
look
sure
forward to
some
any
people will
feedback.
bitch at me, but that's how I have always, that's at least my interpretation on the isotopes. And again, the hydrogen isotopes, please don't do bulk extraction of fluid inclusion waters, even if it's easy. That gives you meaningless information. If you Google meteoric water orogenic gold and find the papers that are still coming out that say meteoric water is important, just look how they came up with that conclusion. It's always bulk extraction of fluid inclusion waters.
Everybody, it's important to read the methodology sections of papers as well. So don't forget. All right, cool. So just to finish up and just close this all out, the one question that I wanted just to ask is, in what ways have magmatic versus metamorphic genesis shaped our exploration strategies for gold? And how important is it for us to be correct in assigning formation? Is it important for research, exploration, or both?
It's for the most part been ignored unless you're a company that buys into what a consultant might tell you, that's saying they can use geophysics to find the right granite or use certain granite geochemistry or geophysics to show you enriched mantle that's going to be area that's favorable for gold. As long as you don't buy into that, even if people are saying there's a magmatic origin, most of the better explorationists for orogenic gold still understand structure is the key. You're looking, trying to understand the evolution of structure, contact between units, dilational zones like bends and major faults where fluids may be concentrated. So I think the exploration community, for the most part, ignores the model idea and knows we're looking for structurally hosted deposits. The magmatic model is rarely used, hopefully, by explorationists, but looking for granites can be important because rheological changes are important. And if you have a competent granite next to a less competent rock, it'll fracture more easy. That's where a lot of the gold may be. Or along the margin to the granite, it may be sheared, and a lot of the gold may be along the margin to the granite. So again, if you're using geophysics and there's old granites that are older than you think your metamorphic event is that form the orogenic gold, targeting those granites still is important because they're great traps. But I don't think the argument has impacted exploration that much as far as source goes, because we're till we're dead, we're always going to argue about where these fluids came from. Because unlike the magmatic deposits, the true magmatic deposits that form close to the surface, these that form deep are more complex. You just don't see the source, and we're still going to focus on the conduits, which are the structure, and the traps, which are the rheological changes or the chemical traps in rocks that we see at the surface now. So I think it's important to understand what's going on to the evolution of a terrain and guide your exploration. So the research is important and how these things form, but really it's tying it to structure that's critical. And I think I'll leave it at that.
That said, I just want to thank everybody for listening to GeoChemist, and a big thanks to Rich Goldfarb for coming on the show, talking with us for such a long time at this point, which I love, dishing some tea, which he actually didn't know how to do. So I'm glad we learned on the show. And really just talking about this hot topic right now in geochemistry with us. I want to thank our sponsor, LKI Consulting, and its Water and Coma Media for our music. And I'm looking forward to chatting with everybody next month. Cool. Thank you, Rich.
All right, I'm glad that worked out, even though I didn't read about dishing the tea. I guess it was all right. I probably should tell Pickthorn to listen to this so he can give me a lot of shit.